All right. Beautiful sun out there, and we're here. Yeah. Okay. Let's get started then. Okay, what happened here? All right. So let me. Okay. Right. So let's see. This is a skill set I posted. Some more, I guess. Okay. Anything in particular you want me to review, or do you want me to solve some problems? Yeah. Review something in DP. Okay. What do you want me to review? Let's be more specific. Just DP in general, or do you want to use as an example some problem, or go over the lecture again? You know, that'll be kind of boring, right? All right. Let me see. DP. Maybe better to solve some problem and then use that as an example to review DP. Is there somebody who has a problem that they would like me to solve? Something from the homework or specific concrete problem instead of just reviewing DP? Okay, so just what is DP, right? Briefly. I mean, DP is smart recursion plus memoization, right? Okay, why do we add this word smart here? Because this part you can do for many problems, right? So every recursion can be memoized. Right? That's not, you don't need any cleverness to memorize a recursion because it's automatic. Yeah? Okay, so the question is, DP is interesting because for many problems or a large class of problems, if you figure out a good recursion, you will see that it can, when you memorize it, it leads to an efficient algorithm. So that's the key, right? Maybe something that I have not done, explicitly in lecture is, because it's a bit vague, is how do you recognize that some problem has some DP solution, right? What kind of problems, right? I mean, how does DP differ from divide and conquer, for example, right? So that might be a good question to ask, right? Let's take what is the first problem that we discussed, which was string splitting, right? Yeah. What is string splitting? I want to know whether a given string W is in a language L star where I have access to a routine which says, is string in L, right? That's a routine which, if you give it a string X, will say yes or no, right? And then you want to know whether I can split W into, whether W is in L star. That means whether I can split W into W1, W2, Wk, where each of them is in L, right? So why is that a canonical DP problem, right? Okay. Well, you can, I mean, so in one way, I mean, in the reason, I mean, a lot of DP problems are defined on either sequences or recursive structures themselves, right, that lead to a natural recursion, and then when you memorize it, you see that it will lead to a small number of subproblems, right? Okay, so you can take some template from it. If you see a sequence problem, maybe I should use DP, right? That's a good practical thing, right? If I have a sequence problem, I should try DP. If it's a tree problem, because I can break up trees, I could try DP because there is a natural recursion, right? More complicated structures like graphs, maybe not so much, because I don't know how to break up a graph in a nice way. There is no nice recursive decomposition of a graph, right? It's complicated structure. It doesn't admit a quick, easy decomposition. While sequences, trees, and simple structures do, right? And because when you decompose them like that, you get the nice structure, which then leads itself to memorization. Okay, but maybe let's do a problem instead of recapping the same old problem from lecture, right? Anyone has a suggestion, something from the past exams or the midterm fodder or whatever? Anything which looked non-trivial? Yeah? Were all of them easy? Maybe none of you actually looked at them yet. That's more like it, right? No. Okay, so I can bring that up. I think, where is that? What do you guys do in the lab today? I don't know what you did in lab. Okay. Let's see, dynamic programming. You want to do number 3, palindromes, or? Yeah? B, what is A? Okay, let me see. Yeah. Sorry? Yeah, of course I know what I'm going to put on the exam. I'm carefully avoiding telling you what that is, right? Okay, you want to do the 3 palindrome thing, or 2, or 1? Which one do you want? Palindrome. Okay. All right. What is? Okay, we can do 2 as well. Sorry. Sorry. Okay. You want to do 3 or did 3? Okay. 3 is what? Palindromes. Okay. When the length of a longest substring of a given string, that is a palindrome, not subsequence. Okay. 3A is just to fool you, right? Yeah. 3A is very easy. Why? Okay. Can you read? Do you want me to zoom it further? Okay. How about, can you actually read it now? Okay. Read 3A. What is it saying? Okay. So everybody knows what a palindrome is, I assume. Okay. Okay. Why is that an easy problem? Uh-oh, you're in trouble. Now, why is A an easy problem? Don't worry about efficiency. I mean, just first cut is, can I solve it in polynomial time? Why is that easy from a polynomial time point of view? You see, you're already in DP world, even though there is no DP needed for this problem. Nothing is needed, just blind brute force, right? You're only interested in substrings, right? Substrings are easy because how many substrings are there? Try all possible substrings, yeah? And check whether any of them is a palindrome. And find the longest one, yeah? There's nothing, no cleverness needed to figure out a solution here in the sense of there's no recursion, all that. I mean, I'm not saying that's the fastest algorithm, right? Okay, is it clear? Substring is a contiguous thing. There are only n square substrings, right? You try all of them. Okay, you'll get an n-cube algorithm. Fine, not great, but at least you know how to solve it, right? Okay, yeah, is that okay? Okay, maybe you want to speed it up, but let's not worry about it right now, right? It's not really a DP problem right now, okay? It's just there to test whether you are able to distinguish substrings versus subsequences. Okay, is that okay? Okay, all right. So maybe we can speed it up. So how is that different from B? Okay, so we also saw, right? Okay, the B is a little harder. What is B? B is, I think something like this was in homework, right? You know, that you're given a long string, yeah? No, it depends on if I want you to speed it up, then you should, yeah, right? Okay, but so the first thing to see is to classify in your mind, what is it something that I can first solve easily, and then can I speed it up, right? Okay, so that from that point of view, A is not very interesting from a dynamic programming point of view. So yeah, there's still the question of how fast you can do it. Yeah, you can do some obvious things, and then you can do something much more clever, but let's not worry about the fine details of that right now. Okay, I want to distinguish A from B because A is easy from that point of view. B is more tricky, right? What is B? B is that I give you a string, right? It's the same question what I did in class, right? String splitting, right? What is it saying? Here, what I'm asking first, I have a long string and I want to break it up into palindromes, right? And I want to break it up into smallest number of palindromes. Okay, well, you know, so here in my original problem I want to give a string and I want to know whether I can break it up into strings which belong to some language. Here the language is palindromes, right? Okay, but for palindromes the answer is trivial whether if you want to just know the yes or no, because every string can be broken up into palindromes, right? Why? Because each letter is a palindrome by itself, so every string can be broken up into a palindrome. So the answer is always yes, right? So it's not an interesting question to ask, is a string, can it be broken up into palindromes? Yeah, sure, yes. So the more interesting question is the optimization version. I want to break it up into the smallest number of palindromes, right? So that's not as easy, right? Because as you can see in that example, there are many ways of breaking it up, right? Yeah? So here, you know, the thing to recognize is that there is no simple polynomial time algorithm that you can think of right away. Okay? You cannot immediately solve this problem as, oh yeah, I can just do it because it's enumeration, or I can do a simple reduction, or, okay? So that's where DP is kind of interesting, right? Because it is able to help us solve problems that are not immediately clear that they can be solved efficiently. Okay? Okay, so it's a sequence problem, so we try to solve it by a recursion, and you assume that you can try DP on it. Okay? To try DP on it, you know, there are two ways of trying DP on it. One is by experience, you immediately see it, okay, which I hope you have some facility by now. The other is, you know, try recursion and then go through the slow process of, okay, can I first solve it recursively, and then I can memorize it and see if the DP will work, right? All right? And the third is by a graph reduction, which I think is a cute trick. I'll show you that too, okay? All right? So many DP problems can be solved by a graph reachability problem, and this too in particular can be done. But that's not really, I mean, it's implicit DP, okay? So, okay, let's solve the palindrome thing. How will we write a recursion for it? So, in fact, I claim I solved this problem for you in lecture, okay? Okay, and he's like, okay. I solved a more general problem, right? I solved the more general problem of given a string W and some language such that I have a routine which is this string in that language. I showed you how to solve the problem of can this string be broken up into k strings that belong to the language? Is W in L to the k, not L star, but W in L to the k, right? So this is, right, if I can solve this, how can you solve this problem? Okay, this is just again algorithmic thinking. I give you as a black box an algorithm that tells me given a string and some number k, whether I can break it up into k palindromes. Okay, and you want to find what? The minimum number of things, right? How will you solve if I had the routine which given W and k will tell you whether W can be broken up into k palindromes, how will you try to find the minimum k? Don't be clever, right? Yeah, try k equal to 1. If we succeed, great. That's done. Try k equal to 2, k equal to 3, k equal to 4, right? And you can go up to k equal to n, right? When the answer is yes. Okay? Or you can do binary search, right? No, not binary search. Binary search won't work. You have to do linear search because it's not a monotone function. Okay, that's wrong. Okay, all right? So you try all possibilities, right? Brute force with a routine, right? Okay? That's another way of doing it, right? So I'm saying it's good to make connections to what you have already seen in lecture, right? Not that, right? But how did we solve that problem? I mean, they're all the same thing, right? They're all the string splitting things out of the form. You know, you define, you know, how will you find it, right? You define this function, right? Min split, right? W, right? So how will you write a recursive thing for it? I mean, W is, you know, assume that W is, I mean, let's say it's, you know, a string is given in this format, right? Okay. Min split into palindromes, right? How you do it? No, I mean, I'm not doing the k. I'm just solving this problem. I want to split it into the smallest number of things directly, right? How will you write a recursive program? Don't worry about solving it efficiently. Just if you have to write a recursive algorithm for it, how will you do it?
You do a min split from 1 to I plus 1 to n, or I is 1 to n.
Okay, but okay, yeah, but no. Are you going to do 1 plus min split of 1 to I and I plus 1 to n? Okay, you can do that. Maybe a little bit easier. Okay, what is the easiest case? When is the minimum achieved? When will you stop, right? Yeah, you know, if n equals to 1, what do you say? Output 1, right? Yeah? Okay, otherwise? Right? Okay? All right? Okay, not mean, let's call this some a, right? You know, a equals to, for simplicity, infinity. It's supposed to be how smallest number of palindromes I can split the string into. Yeah? All right? So you can do this, right? You know, min a. So you see, so W. See, I have a long string, right? I want to split it into palindromes. So what can I do? I take, you know, I can break this into palindrome. If this is a palindrome, then I break this into palindromes, right? Yeah? Agreed. And I try all possibilities. I'm doing brute force, right? You break, you take the first portion, which is a palindrome, and then break the rest in optimally, right? Try all possible such splits and take the minimum. Yeah? Okay? All right? That's all I'm doing. I'm not doing anything clever, no? I'm saying, you know, how can I split W into palindromes? I first take one palindrome, the prefix as a palindrome, and then the suffix I have to split into palindromes, right? Okay? Okay? So that's what I'm saying. Okay, I mean, this code is a little, if A1 to I is a palindrome, what do? If it's not a palindrome, I can't split at 1 to I, right? Yeah, then I say, yeah. Yeah, A is min of AI plus 1 to n, right? Yeah, I mean, it's a long code, but you see the idea, right? Either I try all possible ways of taking a prefix, which is a palindrome, and split it optimally, right? Since I don't know, I try all possibilities, right? 1 to I plus, 1, 2, 3, up to n minus 1. Yeah? Agreed? Yeah? Okay? Okay, the recursion is like a humongous recursion, right? But we are interested in what would happen if you memorize this recursion. Okay, what will happen if you memorize this recursion? So look at if I had a string, let's look at an example, right? What strings are we going to generate when we do this? So if we started out with what is the example here? I don't see it. Banana. Okay. Baba sees a banana, right? Okay. So, think about what the recursion is basically doing. It is not doing nothing very interesting, but I say, it's Baba sees a banana, right? Oh, this is a long string actually. Okay? So, this problem is going to generate a huge number of problems, right? Yeah? But all of them are nice. Why are they nice? What problems am I going to generate, right? B, I'm going to split B, that is a palindrome, right? B is a palindrome, then I have to split this entire Abbas is a banana, yeah? That's one problem that is recursion is generating, right, at this level. The next one is, what is the next one? Because B is a palindrome, right? What's the next one? Well, Bub is a palindrome, right? Yeah? So Bub will, and then Bus is a palindrome, right? And so on. Okay, fine, there are lots of problems. But you look, it's easy to see that in this whole recursion, the only problems that I'm generating are suffixes of the original string, no? Okay, how many of them are there? N of them. So if you memorize it, it will be polynomial time algorithm, right? Yeah? N is the length of the original string. Okay, see, this recursion is generating very simple sub-problems which are not complicated, but they're generated again and again and again and again, right? Yeah? Alright? Alright, is it okay? Okay. Another way, after some point you should mechanically think, oh, this looks like a one-dimensional problem, yeah? Maybe it's not, maybe it is, right? If it's a one-dimensional problem, then, if it is really DP, it should be the case that my sub-problems are going to be of the prefix or a suffix, right? Okay, from this, you can see what the structure of the sub-problems is, right? What is the structure of the sub-problems? At any point, it is I to N, right? Or if you want to think of it the other way, 1 to I, right? 1 to I goes from 1 to N, right? Okay, those are the sub-problems. Those are the only things that we're interested in, right? So what are the things that we're interested in? After we look at this, we define this, for example. Opt of I is min number of palindromes needed to split W1, W2 up to Wi. I am doing the prefix, suffix is also the same thing, yeah? The min number of palindromes needed to split the string W1 to Wi, right? So what is opt of I from our recursion? I'm doing the other way now, but it is the same thing. Min over 1 less than j less than I, yeah? Opt of j, that means we split 1 to j optimally, plus, I'm going to put it in a compact notation, wi to wj to wi is a palindrome, right? This is a strange notation. What I'm saying is that you do the min over all j such that wj to wi is a palindrome. If that is a palindrome, then you look at opt of j, right? Okay, maybe this is not a good way of writing it. Let me write it again. So you write it like this. Opt of I is min 1 less than j less than I Wj to Wi is a palindrome, 1 plus opt of j. Okay, does it make sense? What I'm saying is, to know what is opt of I, what is opt of I? The minimum number of palindromes needed to split the string W1 to Wi. What is it? It is the minimum over all j, opt of j, that is we split 1 to j optimally, provided j plus 1 to, sorry, it should be j plus 1, j plus 1 to I is a palindrome, okay? Yeah. You can do it other way too. You can also do it this way. This is another way of doing the recursion. It's except that it will be a more complicated, okay, no, let me not confuse you, okay? This is fine? Yeah? Okay, but you can directly come to this because you've already had experience with string problems and guess it, right? Oh, it's a one-dimensional problem, I should look for something like this, right? Or you go through the slow route. You say, okay, can I write a recursive enumeration type program for this and then memorize it? See, look, DP starts with brute force, okay? This is brute force, right? I mean, isn't this brute force? Yeah? Okay, this is just basically brute force expressed in a recursive fashion. And then we realize, this brute force has nice structure because, well, it's a sequence problem, right? And the structure of the problem is simple enough that, in fact, the problems are overlapping and I shouldn't recompute them and identifying that structure. Yeah? Right? But you do need to take the step of converting that brute force into understanding that the brute force here can be simplified, right? If you don't, you are not able to see the technique then, right? If you just say, any brute force would be, any brute force cannot be converted into a nice memoized their structure and so on, right? Here we are identifying that, the number of problems we are generating is small when I look at the input size, right? If you try to do it with some arbitrary problem and do a brute force, the number of sub-problems you'll generate will be exponential in the input size. Here it is not exponential. It is polynomial in the input size. It is only n problems we are generating. But we are generating them again and again. Okay? Is that okay? Yeah? Okay? Okay, so here is another cute way of doing it, I think. But, I mean, the thing is, you see that, once you see, that's also DP. You can do this, right? Baba sees a banana. You're really, some people find this easier to do, right? So what you can do is, you can create a graph from this. Okay? How do you create a graph from this? What are the edges of the graph? Okay. So from here you can put an edge to here. Why? Because this is a palindrome, right? And from here, for example, you can put here, and from here you can put a dummy node here, right? Because this is a palindrome, but you can put other things too, right? From here you can put an edge here because BB is a palindrome, right? And what else can I do, right? I can put an edge here because B is a palindrome. I'll have always these edges, okay? So what is the meaning of this edge? This means that in between is a palindrome, right? If I put an edge from here to here, it means that in between is a palindrome, yeah? Yeah, I have to think, am I doing the right thing? Okay, so what am I doing here? I put B to S here. What do I mean? Okay, I'm not being consistent, am I? Okay, all right, so I should do a little better. Okay, all right, let's cut this out. Okay, all right. Okay, how should I do this? Baba, okay, I have to. Okay. I mean, I didn't think through this clearly. You get the idea, though. Okay. So, okay, each vertex corresponds to a letter. Okay. You put an edge like this if this is a. Okay, let's see. I have to put an edge from B to U. That because oh, I think that was okay, no? Did I make a mistake? Baba sees a banana. No, that was okay. Okay, okay. I need this. Okay, that's for sure. Okay, what is the meaning of this edge? Okay, I'll now. Okay, I create a one per letter. Okay, and I put an edge from here to here if the letters from here to the one excluding that is a palindrome. Okay, so I put B to S because Baba. No, that's the wrong. Yeah, okay. Okay, no, that's clearly not a palindrome. The mistake was not that. Yeah, so I should put from B to B. Yeah. Okay. All right. Okay. B to B and okay, that was wrong. Okay. All right. Okay. Okay. All right. I to J. Okay. More formally, VI to VJ is an arc if WI to WJ minus 1 is a palindrome. Okay? Is that all right? This is just an abstract figure. Okay? And now what should you solve in this graph? Shortest path from this end to the dummy node, right? That will give you the number, right? But really you're doing the recursion and memoizing and all that stuff, right? If you can figure that out, you have already figured out the DP. Okay? But maybe some of you like graphs and it's easier to see. Is it okay? No. Okay, so is the graph reduction cleared or no? Yeah? Okay, right? We created a graph out of this string and the edges are forcing it to be a DAG, right? Yeah? And what does this edge mean? That a path in this graph is a split into palindromes, right? Yeah? A path in this graph from here to that must be a split into palindrome. Yeah? That's another cute way of doing it. Yeah. But really, there is a strong connection between dynamic programming and DAG, so that's not surprising that you can do this. Yeah. How many of you have read that section in the notes? No one has read it. Okay. All right. Okay, any other questions? Was that enough review for DP? Yeah. This is the shortest path because you're trying to minimize here, right? Sometimes you want to find the longest thing, right? Because maybe that's your objective function. You can also solve the longest way of splitting it into palindromes, right? I mean, in this case, you know the answer, but suppose I say the following. It's an interesting problem, right? I give you a string and some language for which you give me a routine that is a string in the language, right? And I want to find the split of the string into maximum number of strings in the language. Now you can do the same trick, and now instead of finding the shortest path, you find the longest path, right? In this case, it's trivial because all the edges are there and you will find n because in a palindrome, the right thing, we already know the answer for if you want to find the longest number. But it could be some complicated language where finding the split itself is non-trivial, right? In that case, you can also solve the maximum number of things you can split into by just the same reduction, or the DP also will work, right? It's the same thing, right? Yeah. Okay. Some other topic? Because we have spent some, I could keep going on DP, but yeah. Oh, layered graphs. So, so maybe this is a good topic, right? That basically, right, layered graphs is in a way, it is a way to create DAGs out of graphs to enforce some constraint, right? So, the simplest example, again, it's in the notes, okay? So here is the thing, right? I give you a graph, right? Directed graph, and I have S and T as before, right? And I want to find I mean, edge lengths can be non-negative also here. Okay, I'm not even constraining it. Find shortest L is edge length. I mean, it just right. ST walk with k edges, right? With at most k edges, say. Okay, somebody ask you that thing, right? Is this question make sense? I have a graph, lengths can be arbitrary, negative, positive, whatever. I want to find a ST walk, not a path. Okay, a walk. What's a walk? I can visit a vertex more than once, right? But I want to use at most k edges. Yeah, I don't want you to use more than k edges. Okay, so this is a nice way to do this is by layered graphs, right? So you create, you're enforcing that constraint by saying, okay, I'm going to create G1, G2, K, and these are just copies of the vertices, right? Every vertex is copied multiple times, right? And you put, this is S0, you can think of this, and so here is U, this is the ith copy of, there's a second copy. This is Vi plus 1, right? So you put an arc between the ith copy of vertex U and a I plus first copy of V if UV is an edge in the graph. Okay? If and only if, yeah? Oh, yeah, no edges on them. Okay? Empty graph except vertices are copied many times. And I'm putting an edge between ith copy of U and I plus first copy of V if UV was an edge in the original graph. Right? If and only, right? And, yeah, sorry? No, I don't want edges within this layer. That's because I'll tell you why. Okay? Okay? This is the construction, right? So now what happens? Now what happens? Look at some copy T here, and this is the kth copy of T, right? Okay. Okay. Now, what does a path in this graph correspond to in the original graph? Okay. What are we doing here? We start as okay. What is this connected to? I didn't tell you. I connect S, the 0th copy of S, to its neighbors in the original graph. The same construction, but it is because it's copy 1. I copy the 0th copy of S to a vertex here if SV is an edge in the original graph. So I claim is that a walk here, a path here corresponds to a walk in the original graph, right? Because I'm allowing you to, I may visit the same vertex multiple times because it is duplicated now. Okay. But because it's a DAG, the only way to go from here to here is using one edge at a time, no? So any path here corresponds to a walk of exactly length k. Yeah? Exactly length k, not at most k, right? Yeah? So if you want exactly k, this is fine, right? This will give you the shortest walk from S to T of length with exactly k edges. Okay? If you want at most, you should allow me to go to tk minus 1, tk minus 2, any of them is fine, right? So you can create a new vertex t prime and connect all the copies of t to this guy, right? That will allow me to use at most, right? Okay. So what this layered construction is doing is preventing you from using more than k edges, because you have to cross one layer to another, you have to use one edge, right? So you can enforce some constraints this way. Okay. So layering is useful, but this is also again dynamic programming in some ways, right? Okay. You can think of this as memoizing the DP. Yeah. Oh, for this, well, first in the exams we typically don't ask, but you can say that by construction the only way, of course it's not right. It's kind of fairly easy by construction to see that any path from this word or one layer to the next layer has to use exactly I minus j edges, right? right? And each edge corresponds to an edge in the original graph. So, I mean, okay, it's not very formal, but that's fine, right? So this construction, you know, I mean, you can be very ultra formal. I can prove it to you very formally by induction on I that a path from S0 to a vertex Vi corresponds to a walk in G from S to V using at most exactly I edges. That's the right inductive hypothesis. In the exam, you don't need to write proofs unless we ask you to. Right. We didn't even force you to write a very formal proof in homework for this thing, so I wouldn't force you to write. But it's kind of good to know. I mean, you know, if you had to write an inductive hypothesis without proof, that is what you would say in layer I, and then you can prove it inductive. It's not hard, it's just painful. Right. No, I mean, the thing is, you know, it's also a skill to kind of say what would the inductive hypothesis be. Okay, it might be routine and it might be painful, but identifying that, that's what I should write down as the inductive hypothesis. Not necessarily prove the whole thing, but yeah, that's not very long, but that's good skill. Yeah? Yeah? No, because I can visit you multiple times, no? Oh, it could, I mean, if you know, if there are negative lengths, I may visit a vertex multiple times, no? I didn't assume that they're all positive, right? Oh, okay, you have to be a little careful. Okay, no, let me give you an example. You have to be a little careful with this, right? See here. Even with positive lengths, you can have this trouble, right? Okay, depends on what you okay. Okay. If I ask you, is there a walk of length 3 from S to T? I mean, is there a path of length T from S to T in this graph? There is? No, path of length exactly with 3 edges. Okay, but how about path of length 5? No, it's not a path, it's a walk. Okay, all right. So in fact, that problem is hard. Is there a path of length K is actually NP hard? Okay, but a walk of length K is easy to solve because of this reduction. Okay, see, I mean, if I give you this graph and give you 5, the answer will be yes, right? Why? Because, you know, there is one. But that requires you to duplicate this vertex, right? This vertex will occur twice in that layer, and that's the only reason you will have a feasible solution. Okay, so it is, you know, what I'm saying is it's not about edge lengths being negative or positive, that this allows you to constrain the number of edges you're using, and you may need to use a vertex more than once, right? Okay, so if I give you this example, the answer for 5 is yes. There is a walk of length 5 between S and T. But you can't tell whether there is a path of length 5 from S to T. That's a hard problem. But walk is easier. Okay? It's not about, yeah? It's a tricky. Yeah. Yeah. Bellman-Ford. Bellman-Ford is exactly this. Okay. Okay. So, see, remember, what does this do? This allows you to compute shortest walks of any given length, right? Not a given length, with any given number of edges. Okay? Okay. So, suppose I put k equal to n minus 1. What happens? If I put k equal to n minus 1, from S, I can compute for every vertex the shortest length walk using at most n minus 1 edges. Okay, good. All right. Okay, And I'm not assuming that they're negative lengths or positive lengths, right? So this construction will do it for you, right? Okay, by putting, I can put k equal n minus 1. So, okay, now let's see. There are two cases. Either the graph has a negative length cycle or it doesn't. Okay. If it doesn't, the shortest walk length with n minus 1 edges is real shortest path length, right? Is that okay? If there is no negative length cycle, I don't need to use a walk of length more than n minus 1, right? Why would I need to do that? Because there's no reason, right? I can reach that guy, there's no negative length cycle. If I have a longer walk, that means it has a cycle, but the cycle is not negative length, so I can cut it out and I'll get a shorter path. So if there is no negative length cycle, finding the shortest walk with at most n minus 1 edges will give me the right shortest path distance. Done. Okay, now I still have to know whether there's a negative length cycle or not. Okay, for that you need to do one more trick, right? You say, okay, for every vertex find the shortest length walk with n minus 1 edges. For every vertex find the shortest length walk with n edges. Okay. If there is any vertex such that the shortest length walk with n edges is less than the shortest length walk with n minus 1 edges, then there is a negative length cycle. Okay? So that means going to one more thing reduces for somebody, that allows me to detect that there is a negative length cycle. And then we say, all bets are off, I'm going home, right? So that allows you to detect the negative length cycle. That makes sense? So Bellman-Ford can be thought of as, I can find shortest length walks with any number of edges using this reduction, and then if there is, I can also detect a negative length cycle using the same idea. Okay? Alright, now you have to convince yourself, why is it the case that if there is a negative length cycle, I will find it by detecting the one guy whose length will reduce. Okay? I didn't do a good proof on that because of my pen. I can do that again if you want, right? Yeah, that if there is a negative length cycle, it means that I can keep going, right? The somebody's distance will keep going down in that cycle, right? As I allow you to increase the length of the walk, I will go around and round and round, and so as I increase the length of the walk, I should get shorter and shorter distances for some guy, right? Right? Eventually, I will detect it, right? You can do n plus 1, n plus 2, n plus 3. And if you're not convinced with n, you should be convinced with n plus 2n, right? Okay, if I keep going, eventually somebody's distance has to go down, right? Because I will go around the negative length cycle again and again. Okay, so I can check, if you're not sure, you can say check with n minus 1, n plus 1, n plus 2, n plus 3, n plus 4 up to 2n. If nobody changes, then you should be pretty sure that, you should be sure that there is no negative length cycle, right? Okay, now the proof is more subtle. It says, even from n minus 1 to n, if somebody's distance goes down, there is a negative length cycle, if and only if. And it's not very hard proof, but you just have to go through the details, okay? Okay, so that's it. The Bellman-Ford is saying, do this for n minus 1. If there is no negative length cycle, that's the right answer. If there is a negative length cycle, it means that you can detect it with doing one more step. So that's one way of looking at Bellman-Ford. Okay, it's the same as dynamic programming basically. Right? So that is just Bellman-Ford. Okay. So why do we have to do it this way instead of Dijkstra's algorithm? Because shortest paths with negative lengths are more complicated. Right? Okay. You can't just you can't grow the ball around the source and keep visiting vertices in that order, because lengths can go down, up, and there's no easy way to find them. Okay. Okay. So in some sense, we are reducing the more complicated negative length problem to essentially a DAG problem, right? Yeah. Because DAGs are easy and there are no cycles in DAGs. Yeah. So that's one way of thinking. Bellman-Ford on what? Yeah, you see, Dijkstra's is, Bellman-Ford is a black box for you. You can use Bellman-Ford to find negative cycles. That's the whole point of learning this nice algorithm, so that you don't have to reinvent them, right? So if you say, you're in somewhere and you want to find, I need to check whether the graph has a negative length cycle. You say, I know how to do it. Okay, Bellman-Ford will tell me whether there's a negative length cycle or not. right? So you can use it as a black box. Right? Okay? Unless you want to somehow have a special case where you want to speed up something and you then have to think about it, right? But you really want to first, right? So the first goal in algorithms is to understand, do I know how to solve the problem, even if it's not the most efficient way, correctly? What is the structure of the problem that enables me to understand why I can solve it, right? Other than just brute force, right? Okay, so you shouldn't overthink it. First idea is like, can I even solve the problem efficiently in the sense of polynomial type? Okay, and then worry about efficiency. Okay, because otherwise you'll put the cart before the horse. Let's say you'll start thinking about efficiency before understanding the problem. Okay. You have to first understand, can I actually see the structure of the problem so that it's very clear to me that I know I have a correct algorithm, and then worry about efficiency. Right? See, that's substring problem for palindromes. You thought it was DP and start thinking about DP before like saying, there's a trivial solution, right? First you have to say, is it simple? Can I immediately see a brute force solution which is easy, right? Try all possibilities, and then start saying, okay, I need to speed it up. Okay, let me see what I can do, right? Right? You have to be a little careful in reading the problem first. Yeah. The runtime of this is what is the runtime of this? Yeah, because it's a DAG. Shortest paths on a DAG, whether they are negative lengths or positive lengths, is simply linear in the size of the graph. Right here, the size of the graph is k times m. K times m. Yeah. So yeah. Second question in fall 2000 what? 16. What is that second question? I don't know if I have it. What is it? Can I? Okay. Fall 2000. Okay, let's see. Let's see if I'm logged into this. No. What is it? Fall 2016. Okay. Can you read it out, or somebody has? Sorry. Okay, 1 second. Yes. Okay. What is this? What is that website? I forget. It is. Okay. This one? Is this what you're asking? Yeah? Okay. Has anyone else solved this problem? Yeah? I mean, what does it look like? Can you read it? Okay. So, okay, so you are given, you start here, finish, right? You want to go using only obtuse angles, right? Yeah? Okay, it's some graph reachability problem. Hint. Okay, now try to solve it. You want to model it as a graph reachability problem. Okay. Okay. Yeah. You want to think about it for a few minutes now that you have a hint? So you want to create a graph using this data so that a path in that graph corresponds to walking along this puzzle along obtuse angles. Okay. Does that make sense? Okay. Now you have to figure out what are the vertices, what are the edges. Yeah. Okay. So what should be the vertices of this graph? Yeah. Okay. All right. Okay. Is that right? Okay. Let's see. Oh, okay. So going from here to here, there is no angle defined there, no? Okay, I mean, see, remember the angle depends on not right. See, so, I guess suppose you go from there to here, you are not allowed to go down there, right? So how will you know that? Okay, but remember, you are reducing it to a graph, right? Okay, so you have to first construct the graph and then forget about how you are computing the path, right? Okay, when you do a graph reduction, the idea is that you create the graph which enforces the constraints for you. The edges should enforce the constraints for you. And then any valid path should be, you're not then thinking about figuring out the path for yourself. You're giving it to a black box reachability algorithm, right? So that's the idea behind graph construction. The construction of the graph should make sure that paths in the graph are valid according to the rules of the game, right? So the same thing we did with the Bellman-Ford or whatever the DAG layer, right? We didn't do any, after we created that graph, we just threw it at a reachability or a shortest path algorithm, right? We didn't then look at, oh, how am I going to traverse that graph? So when you do graph reductions, the construction should enforce the constraints you want. So you have to be clever about constructing the graph, not using the algorithm afterwards. Because after that, you're going to use a black box algorithm which won't tell you anything other than just S can reach T or I find the shortest path, right? So the construction is what you should be clever. So you should model the graph in such a way that if I go from this to this, it should be an obtuse angle. Okay. So maybe, okay, hint, I haven't solved this myself yet. What if I make the vertices the segments? Okay. Okay. I'm just guessing, right? So suppose we put one vertex per segment of this puzzle. Okay. Okay. Then, I mean, going from this segment to that segment, I mean, we can decide whether that, I mean, going from this segment to that segment means that I'm going to go between these two segments. Right? That we can decide whether the angle is obtuse or not, and put an edge between them only if the angle is obtuse. So in that graph, I will create, okay, suppose I have a vertex for this edge and a vertex for that edge and a vertex for this edge, this segment, not edge. I won't create an edge between this segment and this segment because going between them is not an obtuse angle. Okay? Okay. So the vertices in this graph will correspond to segments. Okay? Edges in this graph will correspond to whether I can go from this segment to that segment. First of all, they have to share a vertex. And if they share a vertex, they better create an obtuse angle. Otherwise, I will not let you go from this to that. Okay? And then I do the reachability. Okay. So just because the picture is telling you that the vertices should be dots and edges should be the segments, you shouldn't fall for it. Okay. That's a trick here, right? The trick is to figure out that the vertices are the segments of this puzzle. And then the edges correspond to the constraint you want to enforce. That is, I put an edge between two segments if and only if they share a vertex and they form an obtuse angle, whatever, right? Obtuse angle. Yeah? All right. I think that will work, but I didn't work. Yeah. Oh, okay. Yeah. Is that clear? Okay. So you have to be little when you're doing the graph construction. You should not do the obvious thing. Okay. That I mean, not you can. You try it, but then you say, that's not working, right? And then you go and say, wait, why did they give this problem? It's still a graph construction. It looks like it. Let's try other possibilities for what should be the vertices and what should be the thing, right? So remember, we did one puzzle when in the very beginning, the vertex was the state of the system, right? Right? What is the state of the puzzle? It is not maybe where I am, but the what segment I came on, right? So far, so that I know which segment am I allowed to go rather than which vertex I am. Because if you only remember how if you're here at this vertex, you don't know how you came there, right? So the state of the system is what is the last segment I came on, which will tell me whether I can go on a different segment or not. That's another way of keeping track of. The vertices should be the states that you should keep track of. Yeah. I am sure they have, he put it, Jeff must have put something here. What is start here, right? So you're given a start vertex or okay. So I mean, okay, it's a little okay. So in general, you have to be a little bit more careful. It's an edge case, right? If you're starting at a vertex, then I mean, maybe this puzzle you are allowed. You're here, and you could have gone here or there, right? Then it's a little bit unclear what I should do, right? So you create a dummy vertex and connect it to the two segments that. Right. Okay. All right. Yeah, you have to be a little careful depending on how the puzzle is exactly specified. He drew the picture with a segment starting, but he actually says that you're given two vertices start and finish. So there's a little bit of like, if that vertex, look at all the segments incident on it, I could go on any one of them in the beginning, right? So if my vertices are the segments, my start vertices are any segment that is incident to that start vertex. So you have to make sure that you allow for that, okay? Sorry? Yeah, so here you want to say, you're creating a graph, right? Okay, what is the size of that graph as of, see, how do I specify this puzzle for you? What is the size of the input? The size of the input is simply the number of segments, right? And their endpoints, basically, right? So, but what is the size of the graph you're creating? Well, one vertex per segment. And what is the size of the graph you're creating, the number of edges you're creating? Yeah, it's important. Good question. Okay. Yeah, so that's a good question. If this graph has size n, what is the size of the graph I can potentially create? N? Why? No, but the worst case, I claim you can create a graph of size up to n square. Why? The number of edges can be large, no? Okay, see, what happens is that you create n vertices because one per segment, no? But what about the number of edges? Yeah, you can create a big degree, no? I mean, so let me give you an example so that it is a little bit more clear. I could have this, no? So what if I had segments which look like this? Okay? Okay, what does it mean, I mean, think of this as a very small angle, this is a very small angle. If I create one vertex for this segment, one vertex for this segment, every one of them will be connected by an edge, right? So if there are n here and n here, I'll create n square edges in the graph I told you. Okay, so I'm saying, suppose my puzzle looks like this. Okay? My puzzle is, many here, many here. What is the graph I'm going to create out of this? Yeah, so I have one vertex per all of them, right? The total of n vertices. But every one of these guys will have an edge between them, right? But that's n square. Okay, so if I have a puzzle of size n, my graph can have size n square. Yeah? And then I'm doing reachability on that. Right? The number of edges could be n square. So that's what describe and analyze means. My running time is n square, right? If n is the size of the puzzle, I'm creating a graph of size n square potentially, and then running reachability on that graph. Okay, it's linear in the graph size, but my graph construction itself is quadratic in the original puzzle size. Okay, that's what it means to analyze, right? I can't ignore the graph size I created, because I created a big graph, right, compared to the original. See, this looks compact while the graph I created is huge. It's, right, you see that? What does the graph look like from this? It looks like a complete bipartite graph, right? I have n over 2 vertices here, n over 2 vertices here, and I have all possible edges between them, right? So the size of this graph is n square, even though this representation is only n. I'm giving you n segments, I get a graph of size n square. And then I run reachability on it. So that's what it means, right? I have to know how big of a graph I created from the original input puzzle. Okay? That's what it means to analyze, yeah. Okay, yeah, see, he said walk because, nothing in the construction, we are going to create an undirected graph, and it's not, I may have to go around, but the reason for that is that a path in this graph corresponds to a walk in the original puzzle. That's why he said walk is allowed. We cannot guarantee that in this path that we won't visit the same vertex again, because we are only walking along segments. Yeah, I may visit the same vertex again. Okay, so that's why it's okay. Yeah, it's a little careful. Yeah. For this? Oh, okay. Recurrence. Can you solve a recurrence? Okay, give me a recurrence. Okay, 2015 exam, I don't know what it is. Can somebody see it and give me the recurrence? It's not too hard. E what? Okay, what is it? Without thinking, you should say the answer for this. Okay, then you're happy. So why do we need to solve it? More difficult ones? Okay, what is a more difficult one? Okay, what is the answer to this? You got 2 minutes. There is no trick here. Oh, the first one I'll tell you. Okay. Somebody wanted another one, so more difficult one. So this is a more difficult one. It's not more difficult, it's different. So yeah, it will take some. What is that? That's also n-log. Right. Okay. You see why? No. Okay. I mean, you just expand it, right? Okay, but then why is it n log n? So you can do it in many ways. You can do it exactly, no? Yeah. So what is it? It's just basically log of n factorial, right? You can do it that way, but I don't recommend that way. Okay, because okay, then draw the recursion tree, right? And what do you put here? Okay, now you have to be a little careful here. Okay, 2, 1. Okay, you have to add this up, right? Okay, so how many levels are there? It is log n minus 1, log n minus 2, da da da. It seems like a little bit hard to, okay. So is it, the thing is, if you go down to n over 2, okay, it's not going down much, no? At n over 2, what is the value? Log n over 2, right? It's still at least roughly half of log n, right? You're adding up log n over 2 times, so it's at least n over 2 log n, right? Roughly, right? And it cannot be more than n log n, right? It's no more than n log n, right? Because the depth is n, each of them is less than log n, so it's no more than n log n. Now you want to say, is it going down? Is it kind of staying steady, or is it doing what, right? You see that it's not going down very fast, right? So that's the easy way of doing it. The more formal way of doing it, if you want to know that, is this is log of n factorial, right? Okay, what is n factorial roughly? If you know the formula, you can do it, but you don't need to know the formula. That's what I'm trying to say. What is Stirling's approximation for n factorial? Just for fun, if you remember. What, anybody knows? Just you don't need to remember it. It's good to know what is roughly n factorial. I mean, why Stirling's formula is famous? It's because it's n factorial is a simple function, right? It's nice to know how does it behave, right? Okay, how does it behave? Let's find an upper bound for n factorial. What is it? N to the n is an upper bound, right? Yeah. Okay. Is it close to n to the n? Is it right? So it's kind of good to know roughly, right? That's why Stirling's formula is interesting. It's kind of fun to remember it, not because it's a formula, but it is how much smaller is it compared to n to the n, right? So it is something like this. There is a constant in front, which I forget, okay? Some 2 pi or something like that. So it is saying that it is not n to the n, it's roughly n over e to the n, okay? See, it's not n to the n because terms are going down, right? Okay. Forget about this term. It is saying it's some n over e to the n, okay, roughly. It's not, that's not even the right answer. This is important. It is 1 over square root n of that. So the right way to understand Stirling's formula is not because it's a formula, but it's saying, it's kind of giving me a very good estimate of what n factorial really looks like as a simpler functions, right? We understand n to the n because that's an upper bound, right? We understand 2 to the n, roughly we understand how that behaves, c to the n. And we understand square root n, right? Okay, so this is saying, n factorial is roughly like this. And there is nothing else other than a constant in front of it. Okay, and that's a very, very good approximation. So it's a way of understanding n factorial in more simpler terms. So that's why you should care about Stirling's formula, not because it's a formula. Okay, but roughly if you take the log of this, you will get n log n, right? Yeah, I mean you can do that, or I don't remember that formula. What I'm saying is that the way to estimate this is to say it's no more than n log n. Yeah, it's at least n log n over 10, right? Because if you take half the terms, okay, so this is a problem that I ask every final, okay, and 50% get it wrong, okay, it always saddens me. So maybe I won't ask it this final. So how does the following function behave? You know this, right? 1 plus 2 plus 3 plus n. How does it behave? Asymptotically. So what how does it behave? N square. Okay, so what about this? What about this? Okay. Do you know the formula for this? At some point you must have learned in high school, right? Yeah? No? Didn't learn the formula for this? Sorry, this one? This one is n to the 4? No, it's not n to the 4. So how did you figure out it is n square, by the way? Because you remember the formula, right? But you see, you can't have it both ways, right? In the sense that if your only way to remember this is by formula, then you should also remember Stirling's formula. But you're not remembering Stirling's formula. Okay, so you shouldn't think of this as n square because you know n times n to n minus 1 over 2. But you should think of it in a more simpler way. Yeah? Yeah, it cannot be more than, see, when I see n to the 4, I get sad. Okay, you know why? There is no way this can be bigger than n cubed, no? Okay, that's what I want you to first get, not whether the right answer, right? But if you say n to the 4, then you're not realizing that this can never be more than n cubed. Okay, every final I ask it precisely to know this question, how many are seeing the big picture, right? That you may say it is n square and make a mistake in the not knowing the right answer, but you should not say n to the 5 here or n to the 4 because I'm adding n terms, none of which is more than n square. How can it be bigger than n cube? Right? You should not say n to the 4, right? Okay, the right answer is different, but if you go way above the obvious upper bound, then you're not summing things properly, right? Okay. All right. Okay, now you know it's no more than n cube. Is it close to n cube is the next question you have to ask yourself. Okay. Why is it roughly n cube? Yeah? Oh, yeah, the Gauss trick. But nah, that's also a tough thing, right? Okay, if you want to, you can do that, right? But then you still have to do the calculation of what is 2 square plus n minus 1 square and stuff. Yeah, so the right way to think of it is, you know, at n over 2, what is the answer? What is the term at n over 2? N over 2 square, right? All the terms after that are at least n over 2 square, right? How many of them are there? N over 2, right? Then it is at least n over 2 square times n over 2. How big is that? N cube over 4, n cube over 8. So the sum is between n cube and n cube over 8, right? So it should be roughly n cube. Right? What is the answer for this? N to the 4th. Okay, if I give n to the 4th, what is the right answer? N to the 5th. Okay, all right. So it doesn't. The asymptotic analysis is easier because you're not thinking about precise formulas, right? You're trying to estimate. Okay, don't use formulas first. First say, you know, how big is it? How small is it? Right? Sorry? 8? No, all I'm saying is, you know, how can I, you know, I claim 1 plus 2 square plus 3 square plus n square is less than n times n square, right? That you agree? Yeah? Okay, it is greater than n over 2 square plus n over 2 plus 1 square. Greater than what? N over 2 plus 1 square plus n square, right? Because I'm taking only some of them, right? I'm ignoring 1 to n over 2. See, I have n terms here, I'm ignoring half of them. So this is greater than n over 2 times n over 2 square, no? Each of this term is bigger than this, no? Okay, there are n over 2 them, so this is greater than n cube over 8, right? Yeah? Okay, another way to do it, which is again, you know, see, you can also approximate this as, okay, what is this? Okay, right, you know, huh? Okay, All right. So if you want to know what is the sum, right? Why do you think it is log n? Because it's roughly, okay. You don't have to remember it. You can figure it out, okay? And this is log n, right? Yeah. Integrals are your friend, right? Don't forget your calculus, right? Okay. All right. Okay. Any other questions? Now, people haven't seen this trick. Okay. You should see this in calculus actually. Right? Yeah. Sorry? Yeah, very old. Yeah.